If you look at the stock market today, you think we are at the absolute apex of human computation. Nvidia is printing money. Hyperscalers are building gigawatt data centers. We think we are building digital gods, convinced that if we just build a fast enough AI, it will eventually simulate the universe. But from a physics perspective, we are just building really fast calculators. And we're about to hit a mathematical wall that no amount of AI can brute force its way through. I spent 6 years as a PhD candidate in experimental quantum physics. I lived inside synchrotrons around the world. And let me tell you, what every physicist knows, but the broader market refuses to internalize. You cannot perfectly simulate an analog quantum universe use discrete digital logic. The mathematics simply blows up. Now, I need to be clear. Wall Street is not ignoring quantum computing. Google, Microsoft, and IBM are pouring billions into their quantum labs. But retail investors and the standard institutional funds are fundamentally repricing the timeline. The real story isn't about which startups wins the hardware race. It is about the fact that the intelligence agencies of the world are already actively pricing in the collapse of global encryption, triggering a mandatory multi-million-dollar infrastructure cycle today. Welcome to Growth. I'm Sean, your guide to money and navigating the frontier of innovation. Today, we are going to strip away the venture capital noise and look at the physical reality of the quantum arms race. We will break down why the first wave of pure-play quantum hardware failed, how the recent breakthrough of logical qubits just turned the fundamental physics risk into an industrial manufacturing war, and why the most urgent investable alpha isn't in the quantum processors at all. It is in the unglamorous physical infrastructure required to keep the digital economy from collapsing. We need to start from scratch. To understand what a quantum computer actually is, we first have to understand why the current AI hype is masking a massive structural dead end. People look at ChatGPT and they think if we just buy enough NVIDIA GPUs, this AI will eventually cure cancer, invent new batteries, and solve physics. This is a fundamental misunderstanding of what a computer does. A large language model is incredibly good at predicting the next word in a sentence based on human training data. But it is not simulating reality. It is just pattern recognition running on a digital architecture. Every computer you have ever touched is digital. Digital means it speaks in binary, ones and zeros, true or false. It forces information into discrete, rigid boxes. But here's the first principle of physics. The universe is not digital. Nature does not operate in rigid boxes. Nature is analog. It is a continuous wave of probabilities. And you cannot perfectly simulate an analog universe using a digital computer. If you try to force continuous physics into discrete ones and zeros, the mathematics simply blow up. This is why the qubit was invented. A quantum computer doesn't use digital bits. It uses qubits. A classical bit has to choose, I'm a 1 or I'm a 0. A qubit operates entirely differently. Through a property called superposition, a qubit is analog. It exists as a probability, representing both 1 and 0, and every fraction in between simultaneously. If you ask a classical digital computer to find its way out of a maze, it has to run down every single dead end, one by one, sequentially. It's fast, but it's blind. If you put a quantum computer in that same maze, it doesn't try the path sequentially. Through superposition and entanglement, it flows the maze like water. It explores every possible path simultaneously, collapsing only on the correct exit. So, why does this matter for capital markets? Why is Wall Street starting to care? Because of the total addressable market of chemistry. Let's say you want to design a perfect solid-state battery or a room temperature superconductor to perfectly simulate the quantum mechanics of molecule with just 50 interacting electrons. A classical digital computer has to track individual 2 to the power of 50 states. This is over a quadrillion calculations just for a tiny cluster of atoms. If you want to simulate a slightly larger molecule, say one with just 300 electrons, a classical computer will need to track 2 to the power of 300 states. To give you a concrete sense, it is a number vastly larger than the total number of atoms in the observable universe. It is physically impossible. You could turn every atom in the Milky Way galaxy into an NVIDIA GPU, and you still couldn't simulate that molecule. But a quantum computer, because its analog nature directly mirrors the nature of the universe, you don't need a machine the size of galaxy to perfectly map that exact same 300 electron molecule. You only need a machine with 300 perfect logic qubits. They are the ultimate simulation engines for the physical universe. The company that controls this architecture gets to invent bespoke pharmaceuticals and advanced materials without ever touching a wet lab. It is the ultimate industrial monopoly. So, if the math is so powerful, why did quantum hardware stocks crash in 2022? Why did the market lose faith? Because Wall Street fundamentally misunderstood the fragility of the hardware. Classical digital bits are robust physical switches. You can run a silicon chip in a hot server farm and it works fine. But qubits are fragile probabilities, and nature hates quantum states. Think of a qubit like a perfectly balanced spinning coin. As long as it spins, it exists in superposition, both heads and tails. But the moment it interacts with the macroscopic universe, a stray photon, a microscopic fluctuation in a magnetic field, or a fraction of a degree of heat, it is like someone bumping the table. The coin falls flat. The wave function collapses. The probability becomes a certainty, and the calculation is destroyed. In physics, we call this loss of information decoherence. Because of decoherence, the industry spent the last 10 years stuck in what we call the NISQ era, noisy intermediate scale quantum. We could build qubits, but we couldn't keep them isolated from the noise of the universe long enough to do deep math. Now, physicists are pragmatic. If you have a machine that is incredibly sensitive to the environment, that it breaks when a magnetic field shifts by a fraction of a percent, what do? You turn the bug into a feature. You stop trying to build a computer and you start building a detector. This is the actual current use case of NISQ hardware, quantum sensing. If a qubit is the most sensitive object in the universe to gravity, electromagnetism, and time, we can deploy it as a hyper-advanced sensor. Today, noisy quantum sensors are being used by the Navy to navigate nuclear submarines deep underwater without GPS. They are being used by mining conglomerates for underground mineral mapping. It is a brilliant use case, but here's the brutal truth for investors. Selling hyper-advanced metal detectors to the Navy is a great defense contract, but it is not trillion-dollar industrial revolution. You cannot simulate a battery chemistry or break global encryption with a noisy magnetic sensor. And this is where the 2021 quantum specs lied to the market. They tried to sell Wall Street the massive, universe-altering total addressable market of general-purpose simulation, while trying to brute force it using sensor-level NISQ hardware. They told investors, look, we just built a 50-qubit processor. Next year, we'll build a 100-qubit processor, then 400. We'll just keep packing them onto a chip, and eventually, the algorithm will work. And they did build them. Some pure-play companies successfully put hundreds of physical qubits on a chip. But they couldn't calculate anything commercially useful. Computation isn't just about how many qubits you have. It is about how many sequential steps of math, how many logic gates those qubits can execute before they decohere and fall apart. Let's say your physical qubit is 99% perfect. That sounds great to a VC pitch deck. But if you have a 1% error rate and you need to run a chemistry simulation that requires just 1,000 sequential operations, your success rate is 0.99 to the power of 1,000. Do the math. The probability of getting the correct answer drops to 0.004%. Real-world commercial problems, like inventing a breakthrough molecule or breaking RSA encryption, don't require 1,000 operations. They require millions or billions of sequential operations. But in the NISQ era, because of decoherence, the qubits would collapse after a few dozen steps. Having 400 noisy qubits doesn't give you a supercomputer. More qubits with high error rates just meant more noise. Wall Street eventually looked at the static, realized it wasn't going to generate revenue tomorrow, and walked away to go buy NVIDIA GPUs. They mentally priced quantum computing as a 15-year R&D project. But while the tourists left, the operators stayed in the lab, and they completely abandoned the brute force model. So, the industry hit a wall. To simulate a better chemistry or break an encryption key, you need a machine that can run billions of sequential operations. But because of thermal noise, the physical hardware was collapsing after just a few dozen steps. If you cannot physically isolate a qubit from the universe, how do you fix the error rate? You abstract it. We stopped trying to build the perfect physical hardware, and we shifted the problem into software. This is the physical birth of quantum error correction. In classical silicon computing, error correction is simple. You just make backup copies. If you want to protect a specific piece of data, the system copies it multiple times. If a power surge causes a 1 to accidentally flip to a 0, the computer simply looks at the backups, takes a majority vote, and instantly corrects the error. But in quantum mechanics, we run into two brutal laws of physics. First, the no cloning theorem. You're mathematically forbidden from copying an unknown quantum state. You cannot make a backup. Second, if you measure the qubit to check if it has an error, you trigger decoherence. You collapse the wave function and destroy the whole calculation. You cannot copy it and you cannot look at it. So how do you fix it? You use entanglement. Researchers realized that instead of relying on one fragile physical qubit, they could take a large grid of them, say 100 noisy, unstable physical qubits, and entangle them together mathematically. Because they are entangled, they share the burden of the information. And here's the genius part. The engineers don't measure the qubits directly. Instead, they measure the parity, the mathematical relationship between the qubits in the grid. If a fluctuation causes one of those physical qubits to randomly flip, the system doesn't look at the core data. It just sees that the relationship between that specific qubit and its neighbors suddenly broke down. The system instantly detects the anomaly and patches the error on the fly, without ever collapsing the main probability wave. That collective group of 100 noisy physical qubits working together to protect a single mathematically perfect piece of information, that is a logical qubit. A logical qubit is a fault-tolerant ghost in the machine. It doesn't physically exist as a single object. It is an emergent property of the software correcting the hardware. And this is why the timeline just violently accelerated. Once you cross the threshold of fault tolerance, once you prove that you can successfully run algorithms on a logical qubit without the error rate compounding, the paradigm completely flips. You're no longer trying to discover new physics. You're just executing a manufacturing problem. To get a more powerful computer, you don't need a physics breakthrough. You just need to stamp out more chips, build bigger dilution refrigerators, and wire up more microwave interconnects. It becomes an engineering scaling function. This isn't theory anymore. We saw the first proof of concept in late 2023, but the absolute watershed moment just occurred in late 2025. Researchers out of Harvard, MIT, and Q-era published a breakthrough in Nature that fundamentally broke the physical bottleneck. They didn't just build a few isolated logical qubits. They used reconfigurable arrays of up to 448 neural atoms to implement the core elements of a universal, fault-tolerant architecture. They successfully executed deep circuit protocols using dozens of logical qubits. And most importantly, they achieved operation below the error correction threshold. They ran these complex algorithms while maintaining a constant internal entropy. In plain terms, the machine was removing errors from the physical system while simultaneously performing arbitrary coherent manipulation of the logical qubits. It was cleaning up its own noise faster than the universe could degrade it. The physics barrier has been definitively broken. Big tech know this. Google, Microsoft, and IBM has instantly pivoted their entire multi-billion-dollar roadmaps to focus strictly on scaling logical qubits. If investors still pricing this as a 2035 curiosity, they are missing the immediate macroeconomic threat. Because when you combine a fault-tolerant logical qubit with the geopolitical reality of the intelligence community, the global economy faces an emergency today. So, what happens when you scale this fault-tolerant architecture? If you have a machine with 10,000 logical qubits, you don't use it to optimize a shipping route. You use Shor's algorithm. You use it to break the foundation of global trust. Every piece of secure data on Earth right now, your banking transactions, the SWIFT network, military communications, and sovereign state secrets, is secured by RSA encryption. RSA relies on a simple mathematical symmetry. It is very easy for a classical computer to multiply two massive prime numbers together, but it is practically impossible for it to factor the resulting number back into its primes. It would take a classical supercomputer 300 trillion years. But a logical quantum computer doesn't use brute force. It uses quantum interference to find those prime factors in ours. The moment a nation-state scales this architecture, global encryption drops to absolute zero. Now, the mainstream media and tech bloggers will tell you, don't panic. A machine with enough logical qubits to run Shor's algorithm, it's still years away. That timeline is completely irrelevant because of an intelligence doctrine called HNDL. Harvest now, decrypt later. This is not some conspiracy theory. This is the explicitly stated threat driving multi-billion-dollar budgets at the NSA right now. Adversarial intelligence agencies, primarily state-sponsored actors, are currently tapping submarine cables and harvesting petabytes of encrypted financial, military, and proprietary AI data. They cannot read it today. It looks like pure static, but they are hoarding it in massive cold storage server farms. They're making a bet that this data will still be highly valuable in a few years when their logical qubits reach scale. If you're a central bank, a defense contractor, or a pharmaceutical company with proprietary intellectual property, you need to internalize this. The hack has already happened. The safe has already been stolen. The thieves are just waiting for the lockpick to come off the assembly line. This single geopolitical reality completely breaks the venture capital timeline. It forces massive, immediate capital expenditure cycle right now. You cannot wait for the hardware to arrive. If you strip away the venture capital hype, what is the actual macroscopic picture here? It comes down to a single systemic vulnerability. The baseline of the global digital economy is not the cloud. It is not artificial intelligence. It is the cryptographic protocol. The US government has already realized this. NISQ, the National Institute of Standards and Technology, just finalized the new mathematical standards for post-quantum cryptography. This forces every bank, every hospital, and every enterprise on Earth to completely rip out and replace their foundational security architecture. This is not a nice-to-have software upgrade. It is a regulatory survival mandate. We're looking at multi-trillion-dollar forced migration just to keep the digital economy from collapsing. And on the hardware side, the smart money isn't gambling on which startup builds the best qubit. They're buying the thermodynamic choke points. To keep these logical qubits stable, the processors must be cooled to 15 millikelvins. That is infinitesimally close to absolute zero. It is colder than deep space. You achieve this using a dilution refrigerator, a massive multi-million-dollar thermal plant. If a hyperscaler wants to build a 10,000 qubit data center, they need to defy the ambient temperature of the universe. The companies that manufacture these low temperature systems and the superconducting wiring that connects them hold an absolute monopoly of the quantum gold rush. The era of RSA encryption is over. It is an engineering problem with an expiration date, and because of the leap in logical qubits, that date will arrive faster than anyone modeled. For the entirety of the digital age, encryption has been the ultimate shield. It dictated how we transact, how we communicate, and how we protect intellectual property. If the shield suddenly breaks, how does that alter the architecture of global trust? The arrival of fault-tolerant quantum computing isn't just hardware breakthrough. It is a civilizational reset. It is a structural repricing of secrecy itself. For 10 years, the public market was distracted by the digital illusion of silicon and burned by the brute force failure of noisy physical qubits. But the moment we abstracted that fragile hardware into mathematically perfect software, the moment the logical qubit was proven in the lab, the timeline violently collapsed. We stopped trying to discover new physics, and we started an industrial manufacturing war. The entities that scale this architecture and control the choke point required to cool it will not just own the ultimate monopoly on chemical simulation. They will hold the master key to the global digital economy. So here's the real question for you. When the first sovereign states finally scales this architecture and powers on a fault-tolerant machine, they aren't going to hold a press conference. They're just going to quietly open the vault. If every piece of encrypted data on Earth now has an expiration date, how do we function in a world where trust can no longer be mathematically guaranteed? Let me know your take in the comments below. This was Sean from BioSpark. If you enjoyed the video, press like, subscribe, and don't forget the notification. And if you want the deep dive report with the full citations and the market breakdown, subscribe to our newsletter at the link below. Thank you for watching. Until next time.